reasoning and algebra and geometry. So we're going to just rehash some of our algebra procedures and talk about essentially why we were allowed to do some of those algebra procedures. And there are things that, guys, you inherently or instinctually, because you've been trained by habit, you do this stuff without thinking, okay? What we want to do now is kind of take a step back, slow the process down a little bit, and actually do the thinking. And say, okay, now what allows me to do what I just did, okay? Because we want to be able to basically have an argument of why something is occurring, why we were able to make maybe this final argument as a solution or something like that. And I kind of draw a comparison that you probably asked your parents at some point for something monetarily, maybe some money. Maybe you wanted to borrow the car, maybe you wanted to take you somewhere, and their answer inevitably at some point was no, and you ask why, and they say because I said so, right? Okay, you've all been in that situation. And that's not a good answer for you, right? All right, when you were in 7th grade and you were told, hey, we're going to do division, but remember you can never divide by 0. My hopes are that at that point you asked why. All right, and they probably said because I said so, because we can't, we just can't, okay? At that stage of your life, you didn't have enough algebra to maybe understand why you can't divide by 0. And maybe right now we don't have enough understanding algebraically why we can't divide by 0, okay? But we'll get there at some point. But there's a lot of things that instead of me just saying, hey, this is a fact, just abide by it, this is the way it is, because I'm telling you this is the way it is, we now have the ability, or we're going to soon have the ability to say, okay, I agree with that. I take your word for it, but now let's validate that. Let's prove that. Let's show that what you're saying is indeed true all the time. And that's what proof does for us, okay? So by the end of tomorrow, we should see kind of a conglomeration of the last 4 sections, 5 sections, and the individual components that were in those kind of structured, and you see the purpose of them as we start doing proofs towards the end of tomorrow's class. But the idea is trying to get you guys to get in the mind frame of, regardless of what class you're in, math, science, English, whatever, when something's provided for you as a truth, as a fact, let's ask the question why. Let's talk about why, okay? Can we validate it? Can we prove that? Can we develop an argument of why, okay? And if we can do that, it's going to make your understanding of those things that you're talking about in those courses so much more broad, so much more a more in-depth understanding, and you'll be able to apply that information later somewhere else a lot better. Okay? You've heard me say maybe before that if we memorize things, our memory is a short-term thing. Okay? That short-term might be 2 weeks, 3 weeks, 4 weeks, might be a year, might be a decade. But eventually, your memory is going to fail you, and that stuff's going to fade, right? Okay? But if we can start developing an understanding of why certain facts are the way they are, that memory won't fade us. And if it does, well, at least we've elongated the time span in which it stays with us. Okay? So that's kind of the hope when we start to build these types of relationships inside proof. These are some equality properties that you guys have known from Algebra 1 for quite a while now, maybe even 7th and 8th grade math. When we give you rules, algebraic rules, we're going to give you arbitrary values. Okay, so A, B, and C up here, they're arbitrary values. They're variable values. They can be anything they want to be as long as they abide by the fact that they're real numbers. Does that make sense? Okay, so any number off the x-axis essentially is what we're thinking about. Okay, and all these rules are applying essentially the most kind of dwindled down examples we could have. Okay, and when we start talking about those ones that I've highlighted there, we've got 3 components. We've got A, B, and C. But that's the most kind of basic example you can get. You can maybe do an A, B, C, D. You can do A, B, C, D, E. You can do A, B, C, D, E, F. You have more options. Does that make sense? So if we can understand it on the smallest level possible, hopefully then we can expand that concept to bigger things. Okay, so the addition property of equality. These are all properties of equality. So these are all values, right? These are all numbers. That's the only set of things that can be equal are numbers, okay? So here's the idea. It's kind of what we were talking about yesterday. If this is happening in front of you, you got these three numbers, A, B, and C, and that's happening in front of you. So let's say, for instance, I say A is 3, B is 3, C is 5. If I gave you that, okay, if that's my second statement from yesterday's law of E-tax, if this is happening in front of you, which is that statement right there, right? Then what conclusion can you make about this information? If I take 3 and add 5 to it on the left-hand side, that's my A plus C. And I take my 3 and add 5 to it on the right-hand side, that's my B plus C. Does that get me a true conclusion still? Yeah. It's not the same as statement 3 equals 3 that I would have started with, okay? But it's still a true statement. It's a new statement that I didn't have at the beginning, but I know now that it's true. Does that make sense, everybody? You've done this before. You have done equations where we say 2x minus 5 is equal to 15. You've done that, right? Okay. And you've added 15 to both sides, correct? Okay. So look at this here. Now, there's a little bit of a reassignment of values here. Let's say it's that set of expressions. So let's say 2x minus 5, because that just represents a number, right? When I know x is, that expression is just a number. Well, let's say that number is A. Let's say this number is B. Is that going to make sense? Okay. So are we saying that A is equal to B here? Does that make sense, everybody? What would you add to both sides of this to start getting something new? You would add 5. So is it then valid to say that my C value of plus 5 here and my C value of plus 5 there should yield me, in this particular situation, it should yield me that, right? Okay. But the reason we can do that is because we started with two things that were equal, A and B, which was 2x minus 5 equal to 15, okay? And we added in the same thing to both sides. So then what we produced is something new, the new fact, 2x equals 20, but it's a true fact. Does that make sense? Okay? And it's simply that idea of, and you guys, you do this instinctually, you've been training this way. If I see minus 5 and I want to basically get that to go to 0, I need to add the inverse value, right? Okay, I need to add 5 to both sides. You guys probably talk about it as opposite operation. I like to use the word inverse operation. Add 5 to both sides, and I get 2x equals 20. Is that okay with everybody? Okay? That's the thing, is that when you're doing that stuff, you've been trained so much to do problem 1, problem 2, problem 3, and get those done fast. And, you go through those steps. Now we want to think about those steps. Think about what is really allowing me to do that stuff. All right? The second one is subtraction property equality, and that's the same idea. Okay? So if I started like 2x plus 5, 2x plus 5 equals maybe 15. Now what would I do to both sides? I would subtract the same amount, right? Okay? So if you start with something balanced, okay, A and B are balanced, they're the same. If I want to maintain that balance but remove something from both sides, I got to remove the same amount from both sides, right? So that's what we're saying. We're removing C from both sides, and you should get something new, something completely different than what you started with, but it should still be balanced. Okay? Addition and subtraction, obviously, they go together. They're inverse operations. We get down to the next two, multiplication and division. The same idea. Okay? You guys have seen, if I have 1/2 x equals 4, okay? So here's my A concept. Here's my B concept. If they're equal, let's take a third value C and multiply both sides by. What would you multiply both sides by here? You multiply both sides by 2, right? Okay? So that means if I multiply by C there and multiply by C there, I should get a result that is still equal. And that's what you're seeing them right here. If A and B start off being equal, multiply by the same value to both sides. In our specific question, we multiplied by 2 to both sides. And you should now get a result x equals 8, which is still true. It's new, but true, right? And that's the idea. When we apply properties, we want to get something new that we automatically know is true. And it's true because these properties exist for all values A, B, and C being real numbers. Okay? The division property, same idea. The division property, though, usually you've probably seen it this way. 2x equals 10. You would divide both sides by 2, right? Okay? You've got an A object here. You've got a B object here. If we divide them both by some C2, or C value being 2, we would get something that looks like this. Okay? So as long as you start with two things that are equal, you can add the same thing to both sides and be okay. You can subtract two things, or same thing from both sides and be okay. You can multiply both sides by the same thing and be okay. You can divide both sides by the same thing and be okay. Is that all right? Okay. These next three that I've highlighted, these are things that maybe are not new, or sorry, not familiar to you. Okay. These might be completely new. All right. When I see the word reflexive property, the reflexive property, all that is saying is that you have a number and it is equal to itself. Okay. Whenever something is equal to itself, we use the reflexive property. Again, you've done this. Maybe you've never been told that you're using the reflexive property. But a lot of you have maybe seen, like if I have 2x, and you probably do this on your own, 2x plus 3, let's say it equals 9. Do a lot of you do this? Right? Okay? You've at least seen that, right? Well, what do I really have here? I'm telling everybody that's reading my work that I'm about to I didn't remove anything yet, right? I didn't really do the calculation. But I'm telling you, what I have over here, that's -3, it is the same as the -3 that I'm going to apply over here. Does that make sense, everybody? And then we go through, and now when I write it this way, that is subtraction. The 2x equals 6 is the subtraction process. This here was the reflexive process, just showing everybody that what I'm about to subtract from both sides is indeed the same amount so that I maintain that balance. That's the reflexive property, okay? Or maybe the only place that you have seen the reflexive property, but never really talked about it, okay? The symmetric property, let's do this question. What's that? You see the symmetric property here. It says if A equals B, then B equals A. So all they do is kind of flip those. Okay? I can basically say, when I read an equation, I can read it left to right, and it be true, or I can read it right to left and be true, right? So you've all been in this situation where we get like 9 is equal to 3x. You divide both sides by 3, you get this, right? But then don't a lot of us flip-flop it like that? Okay? So the idea is if 3 equals x, then x equals 3. We're allowed to flip equations like that and maintain the same truth. Okay? That's the symmetric property, just flipping something. Okay? One way to recognize the symmetric property sometimes, especially if it's written kind of like it is here, okay, in kind of a linear fashion, if I folded between the H and the E, would that B fall on top of that B? Would that A fall on top of that A? Okay, so the left-hand side falls on the, basically the left-hand side of this equation falls on the right-hand side of this equation, and the right-hand side of this equation falls on the left-hand side of that one, right? That's the idea of symmetry if we think about like lines of symmetry for your body or lines of symmetry for shapes and stuff like that. Basically, one side falls on the other when you fold it, right? Does that make sense? Okay. So you can maybe recognize the symmetric property occurring that way. And that's what we're going to try to do a lot of times, guys. Is we'll be given an example, algebraic or geometric, and we're going to try to figure out what are the properties, what are the theorems, or the postulates that are allowing us to make these statements. So we have to be able to kind of recognize what's going on, what they're doing. All right. Transitive property. Transitive property is, let's say, that Trey, Alex, and myself are all on the same curling team. Okay. So let's say that. Do you have any idea what the people's names are when they, like, what positions they are when they're curling? I want to be a brusher. Okay. So let's say that everybody know what curling is. That's what so they throw that big stone on ice and then they polish the ice in front of it so there's no friction or to minimize friction, that kind of stuff to get to move. So let's say that all three of us are, let's say I am as good of a scrubber or a broomer, whatever they call them, as Alex is. And Alex is as good as Trey is. What's the argument that you can make about me and Trey, even though I never linked me and him directly? We're just as good, right? Okay. So the idea of the transitive property is that A equals B and B equals C. Okay. So Faye is the same as Alex, but Alex is the same as Alex here is the same as Trey. You can make the link that say is the same as trade. Does that make sense?
Do you think that we can make a deal with it?
We probably could, yeah. Okay. So that's the transit process, but it's working right here with numbers, okay? Because we've got that equality idea. So let's say that Mr. Fay's math grade is the same as Alex's math grade. Alex's math grade is as good as Trey's math grade. What's that tell you about Mr. Fay's math grade and Trey's math grade? I'm as smart as you are. We got the same math grade, right? Okay. So compliment for you, insult for me, right? All right. So that's the transitive property that works there. Okay. Now, the transitive property, guys, is something that we can actually kind of progress even further than just three objects. If I go down, open this up here. Let's say right here I give you these ideas, these items, okay? A is the same thing as B, but B is the same thing as C, and C is the same thing as D, and D is the same thing as R, okay? Do you see how when we write that A is the same as B, and B is the same as C, that this grouping of terms right there, that B is kind of a middleman, right? Does that make sense? That's the link that connects A to C. So if I get rid of those, I now from that have A is the same as C. Well, if I look at that one and that one, is C the middleman there? Does that make sense, everybody? So I get rid of those, and now I've got a new argument that A is the same thing as D. But if I look at that one along with this one, is D the middleman? So what's the final argument? A is the same as R. A is equal to R, but R is 12, so there's the middleman of R, cancel out. A then is what? 12. Okay? Then that tells me if A is 12, and I go through that progression that B, C, D, and R, they're all related to one another, they're all equal to one another at one point. Aren't they all 12? Okay, so this is the idea of transit property. Usually we see it in three, especially early on, we see it with three objects. Okay? But we can, I think we got 5 or 6 up there right now. Basically what it says is it's going to take a collection of things. And that collection of things, we're going to see a bunch of congruencies, and they're going to link together. And basically that description right there tells you that those 5 or 6 things are all equal. So doesn't it make sense I can pick out any 2 of them and say any 2 of them are equal? If I said all of your guys' math grades are 98, every single person has a 98%. Can I take any 2 of them and say that any 2 of them are the same math grade? Yes, and that's kind of what the transitive property does for us. Now, what becomes a problem for us is that this is very kind of procedural or a very linear progression, right? A to B, B to C, C to D, D to R, then I get A to R, right? A lot of times, we're going to see it this way, where we have a bunch of equality statements, and we want to come up with kind of an overall new statement, okay? And they're not in a progressive order like they were in the last one, okay? Not a linear order, especially in the last one, it's kind of, more alphabetical than anything. But you start looking at it, and if these are all true, so these statements are all true, can I take B equals C and come down here and look at another statement that either has B or C in it, right? So there's some options here. I'm just going to look at this one. Those two together tell me what new fact? C is equal to A. Okay, so C is equal to A. So now that I've got it, those 2 things were true, and they were true, and we use them together, kind of like the, the law of syllogism, right? We use those together to come up with a new fact that we didn't have already, okay? But we now know that that new fact is already true. Does that make sense? So C has to equal A. Now, if C equals A, let's do this again, okay? Are there any other items in this list that have C or A in them? And we've got there, right? So now what's the link there? Well, that's saying C is equal to D. But that's not new, right? We're looking for something new. Huh? That's not new. If I look at these 2 things, put those together, and what new fact do we get out of that? Okay, A is equal to D. Notice how A is equal to D is not in any of this stuff right here? But if I combine those 2 with the transitive property, now we can say A is equal to D. and it's new, and it's true, and I just wipe those away because I'm done with them right now, okay? At some point, maybe we use them over and again, or over and over and over again, however many times we need to, but right now, this one, it's enough just to cancel them out. I don't want you looking at those anymore. So now look at this end. This one has D in it, right? That one has D in it, right? So what can I say about R and A? R and A are equal. Wipe those out, done with them. Now, R and A are equal, and R is 12. What's that tell me about A? A has to be 12, okay? So as we start doing proofs, the equality statements that you get that you're going to have to use a transitive property with might not come in order, all right? You might have to reposition them. You can reorder them if you want to. You can, it might make sense at some point, okay? If this is R equals 12, can I rewrite that as 12 equals R? And we should be able to know that we can do that because that's the symmetric property, right? Allowed to flip any equation I want to and still get the same result, okay? You're allowed to do that, okay? It makes sense to do that. Here's what I would maybe do. Let's take this one here and rewrite it. Rewrite it as C equals B, right? Because that now make an easy progression right there. C is equal to B, but B is equal to A. Does that allow me to easily visualize that C is equal to A? So that might be a reason why maybe we can use the transitive property and the symmetric property together to kind of make these links a little bit more concrete to it. Substitution, okay? Substitution. So let's go back to our kind of sports analogies. Let's say that Mr. Wiggins and myself are both pretty good soccer players, okay? He gets tired. We're both the same. We play the same position. He's as good as I am. I'm as good as he is. He gets tired. What's the coach going to do? He's going to take him out. He's going to put me in, right? Okay? He's going to replace him. What do they call that? What do they call me? Downgrade. A substitution, right? Not a downgrade. A substitution, okay? So I'm a substitute, right? Substitute teachers. They replace the teacher, right? Now, in some aspects of everyday life, we use that word in like a substitute. They bring a substitute teacher in here. They're probably not going to be at the same math level that I am, right? Okay, or teach the same way that I teach, exactly the same way. In sports, the idea is we'd like, as a coach, we would like those substitutions to be an even kind of thing. But we know a lot of times, if you got a starter, there's a reason they're a starter, right? And you got a sub, there's a reason they're a sub. They're probably not the exact same level of skill. But mathematically speaking, guys, when we substitute things with their equals. Does that make sense? Okay. So you've seen this before. If I have like 2x plus 3y, and I tell you x is 5 and y is 2, would you rewrite that as 2 times 5? You replace x with its equal of 5? And then you would rewrite 3 times 2, because now you replace y with what it is equal to the value 2. Does that make sense? That's substitution. It's replacing something with its equal. Okay? Now, how's that different than what we talk about in everyday life? Is that we replace it exactly with what it was equal to. I didn't replace the x with 4.99, something a little bit less skilled than 5. Does that make sense? Okay? But you hopefully maybe use some of those everyday concepts of how we use those words to kind of make an understanding of how we use them in math. Okay? Is that all right with everybody? So those are hopefully some terms that maybe you have some experience with. Let's go. There's a couple more here on the next slide. I believe the next one is distributive property. All right, so distributive property, guys, let's say that I am a paper boy, and I have to go door to door and hand out a newspaper, right? What's another word for doing that act, where I go door to door and give somebody a mailman? I pass out. What's another word for passing out or delivering? Distributing, right? Okay, so I am delivering or I'm passing out that value of A up there to kind of a neighborhood, the B plus C, that's the neighborhood, right? Does that make sense? Okay, those are the people in my route. So I'm going to pass that A through to that and to that. But the operation that we use to do that is multiplication, right? So distributive property is just a fancy word for multiply, okay? But you're going to do it multiple times, correct? You're passing that value of A through to multiple things with multiplication, okay? That one on the right-hand side just talks about the difference, okay? If I distribute that A, I got to pay attention to the minus sign, right? Okay? Here's a question that I have for you, okay? And this is where this might help you realize what we're trying to do with proofs. You guys know that when I have 2x plus 5x, okay, if I gave that to you, so that was given, you don't have any need to prove why that is what it is. What is the next thing you would probably do algebraically? You would probably add them, right? You would probably make that 7x. What would be the logic reason that you tell me why I can do that? Huh? Because I said so, or you said so? Or they have the same variable, okay? So we are... Would you guys say combine like terms is maybe that reason? Okay, so now what we have to do is, okay, well, what does like terms mean? Okay, if you see, what if I had like 2x plus 5x squared? Because I get a lot of people, and this is the reason we sit down and we discuss this and we think about this, because at some point you're going to get good at this, and hopefully you already are. But then you're going to get a question like this. And people want to automatically say, well, I'm going to add those together and get 7x squared or 7x cubed or something like that, something silly. But you can't. And I want to know, well, why can't I do that? Okay? And your answer might be, well, they're not like terms. You were told in Algebra 1, maybe 8th grade math, whenever this was first introduced to you, that it's combining like terms. You basically look at do they have the same variable, and do the variables have the same exponent? It's kind of the identifier we use. But we were never explained to why we can do this. Okay? It's distributive property. Okay? If this is, what distributive property is multiplication, right? What undoes multiplication? Division. So multiplication and division undo each other, they're inverse operations. That means if distributive property is multiplication, and multiplication has an inverse, then division has to have some other name for it. Does anybody know that other name for division that we do with multiple things? Like if I started on this side here, and I wanted to get back to that, okay? It maybe you recognize it with it. If I had like x plus 3 and x plus 2, you would FOIL that, right? Well, FOILing is just an acronym. It's a mnemonic device for distributing twice, right? Distribute the x to everything over here, distribute the 3 to everything over there, right? What went with FOILing? What process went with FOILing? The FOILing is multiplication. If I started with x squared plus 5x plus 6, and I wanted you to get back to that, you guys remember what that's called? Factoring. Okay? Factoring is a fancy word for dividing. Does that make sense? Okay? So distribute, fancy word for multiply. Factor, fancy word for dividing. If I gave you the number 12, and I said one factor is 2, how do you get the other one? You take 12 divided by that factor of 2, right? It gives you 6. So factoring is division. So let's look at it. Let's talk about why this is 7x. Can you divide that by x and that by x? Does that make sense? If I do that, I'm going to divide it, but I don't want that value to change. I want the expression to be ultimately the same quantity. So I don't want to get the x, I don't want it to disappear. But what's 2x divided by x? 2. What's 5x divided by x? 5. Okay? So this here is the same thing as that, right? Just reorganize. Well, doesn't that allow me to do this addition now? What's 2 plus 5? 7. So now what's x times 7? 7x. Okay? So what allowed us to say that when I get 2x plus 5x, I can change it to 7x? It's ultimately the factoring and distributive properties, right? Does that make sense, everybody? Okay. Now we encompass that and we wrap that up as an ASCII to say it's combined like terms. Okay? But now we know why we have that phrase combined like terms. And that's what this class is going to be about, for the most part, is here is two angles that are congruent. But then you ask, okay, why are they always congruent? Okay? If I tell you have base angles and isosceles triangles, they're always congruent. You should be able to say why. And we should be able to go through a step-by-step process that explains they're congruent. So I can do this, I do this, I do this, and I do this, and that's always going to show out the set of angles that are congruent. Okay? And that's what we're kind of focused on early on in this course. So we're always trying to address that question, why can we do something or why do we do something? Okay? In your homework, if you were to have something like that where it looks like you're going to take 2x plus 5x and rewrite it as 7x. Or here in this example, I have 2x plus 30 plus x equals 180. You would probably rewrite that as 3x plus 30, right? 3x plus 30 equals 180. You're going to be, in your homework, there's going to be a drop-down window. So that's my drop-down window, right? I click on it. I'd be looking for the combined like terms statement, right? And it's not going to be there because combined like terms is ultimately a distributive property. Does that make sense? You guys have heard, like maybe if you got younger siblings or cousins or whatever, they're in the middle school and elementary now, they're doing the Common Core, and they say the math that they do is completely different than the way I learned it, right? And parents are struggling with that and they're having big fits about it. You may hear that? Or maybe you guys experience some of that. The reason that they're struggling with that is because at that level right now, they're trying to teach kids this concept of distributive property. Okay? They're trying to teach them numbers with factors inside them and how I pull those factors out. And I can do that addition or that mental math maybe a little bit easier. And I have understanding of why we can combine like terms. So they're creating procedures and processes that hopefully instill that concept into us. So when they get here, we don't have this discussion today. Does that make sense? It's already built into them, trained inside them to be successful when they get here in this concept. All right? But parents are kind of flipping out about that or have been flipping out about that because that's not the way they were taught. Okay? So it's kind of foreign to them. All right, so when we talk about properties of equality, that's awesome. That's referring to values, referring to numbers. We also have properties of congruence. Okay? So properties of congruence. Now remember, this is not talking about numbers anymore. It's talking about shapes. Okay? The first one is the reflexive property. And these were the same properties that we had with equality, right? There's a reflexive property equality, there's a symmetric property equality, there's a transitive property equality. These are really viewed the same way, but I want you to understand, because they're shapes, we're kind of think about them in our minds a little bit differently, okay? When they're shapes, when I say AB is congruent to AB, that's the idea. If I tell you to draw a segment on your paper, label it AB, can you, no matter how big it is or how small it is, can you always cut and paste that picture and put it back down on itself and they match up 100%? Okay? Any segment is always congruent to itself, right? Any angle is always congruent to any angle. Any angle is congruent to itself. You can do that all the time with any shape. And right now, the only shape that we can do congruence with, because congruence is two aspects, right? It's got to be the same shape, same size. There are only two shapes right now that we can measure and determine the size for: segments and angles. We can't measure lines. We can't measure rays, because they go on forever. Okay. The symmetric property. If I tell you, hey, AB, that segment is congruent to CD, you can reverse it and say, no, CD is congruent to AB. We both be right, correct? All right. We've talked about the symmetric property kind of when we identified segments. If I call it segment AB, can you call it segment BA? That's kind of a symmetric idea, right? I can go from left to right or right to left and get the same result, the same object. Okay. So symmetric property of congruence exists. You can flip-flop them and talk about them in any order that you want to. And the last one's the transitive property. Okay. So if I have, look up there on the whiteboard over here. Okay. If I've got that purple segment congruent to the black one, and then I tell you the black one is congruent to the blue one, what can you tell me automatically about the purple one and the blue one, even though we didn't talk about them? They're congruent as well. So it's the same transitive aspect, the same understanding that you use with A, B, and C numerically. It's now shapes. Okay. And the idea is that I should be able to cut and paste that purple one and put it on top of the blue one. All right? So remember, talking about congruence, it's always a shape aspect, a shape idea. when we're doing our homework, okay, and I recognize transitive properties occurring here, do not click your drop-down box and just go look for the first word you see transitive and select it. Because transitive property of equality will be in that option, and transitive property of congruence will also be. So you got to know which one you're talking about. If it's an equal sign, it's equality. If it's a congruent symbol, it's congruence. Okay? It should be pretty self-explanatory there, but a lot of people miss those throughout the year just because they're in a rush. They don't read the whole result, the whole option, and they click transitive property of equality when it should have been congruence or something like that. All right? We already talked about that. Let's get to this. So these are just some examples. Okay? So in the next 5-6 minutes, we can finish these examples up and be done. So 2x plus 9 equals 19. This is what your homework is going to be structured as tonight. And you're going to find out then, after we do a handful of these tomorrow, we're going to come over tomorrow and we'll be working inside one of these things, which is a proof. Okay? And these regions over here will be all these properties and maybe some postulates and theorems and definitions that we've talked about this year. Okay? So we're doing kind of individual statements now and get a good hang of those. And then we'll progress that and do a proof with 3 or 4 of them, and then do one with 5 and 6. Kind of stagger things so we develop an initial understanding, and then as the questions get more difficult, hopefully we can address those maybe easier. I'm going to tell you this first thing here, and this is going to be in your homework. Okay, that's given. Okay, that is what is happening in front of you. If this was an if-then statement, it would say if 2x plus 9 equals 19. Okay, remember that would be what you know to be occurring, right? That hypothesis is happening in front of us. Then 2x equals 10. Okay, so you might see it written in your homework this way. If you're a person, I'm a person that prefers it like this, because that's how I would do the algebra, right? Okay. If you want to take a phrase like this in the if-then statement and rewrite it this way so you see what maybe that step is, by all means go ahead and do that. But what do they do from step 1 here to get down here? Or what do they do in the if statement to get to the conclusion statement? They subtract it, right? Subtracting 9 from both sides. So that is the subtraction property of equality. Okay? It's the property of equality because it's the equation. And it's also that understanding that we can only do subtraction with numbers, right? So it has to be equality. Okay? So the next one, part B here, this is given. We have these 2 relationships between OW and W and L. Okay? What then allows us to make this new statement that we know automatically to be true, even though O and L have never been related directly with one another. Huh? Yeah. That's the transitive property. Okay. Now, is it transitive of equality or congruence? Yeah, property of congruence. And so what they're saying here, if I were to cut out angle O, it's going to land on angle W. Cut out angle W, it's going to land on angle L, right? So then that tells me that I could have cut out O and put it right on top of L. Not even knowing any other measurements or any numbers that are associated or characterize those shapes, we can do that. Okay. Something that I like, guys, is that thing. Kind of write it this way. I can see that W is the link, right? Or the chain that brings O and L together. Or if you think about it as kind of the middleman in a transaction. If there's a middleman in a monetary transaction, I probably want to get rid of him. Does that make sense? Okay, because I'm paying him to do something that could be done myself. Okay. So if we have transactions that have middlemen, we like to get rid of them. If I were to get rid of those middlemen, what am I left with? Just O and L, right? So we can make that argument that O is congruent to L. That's kind of a way I like to visualize and think about how the transitive property is occurring and what I get from that transitive property. Here, letter C, if that's given, it's going to allow me to just kind of flip-flop these things. If I had 4 equals x, what allows you guys to write that as x equals 4? Starts with f, symmetric. Okay? So it's a symmetric property, and it's of equality. So now, here's the thing, guys. We don't have numbers here, right? There is not a number being presented to me visually. When I say M angle T, or measure of angle T, it's a symbol that is representing some unknown number behind it. Does that make sense to everybody? Okay? That's like when I write down this symbol, there's a known number that's hiding behind that symbol, right? 3.141, whatever. Okay? So when I see measure of angle T, measure of angle E, we're saying that there are two numbers here that are equal. Okay? We just don't know what they are. And we're going to do that a lot this year. Okay? State that two numbers are equal, even though we don't necessarily know what their individual values are. This one here is similar to the last, not the last one, but the one before that. Okay? That's given, did we just flip-flop these? What's that flip-flop allows? What's the property allows you to do that? Symmetric. Now, is it property of congruence or equality? Yeah, congruence. I'm not going to write it around our room, but property of congruence. What's happening if this is given? What happens here? That's distributed. Okay? Now, distributive property is a property of equality. Okay? Congruency does not have a distributive property. Part C here. Okay? Now, there are two options here. Math Excel is going to kind of direct you towards one. If you had, think about this, if you had 2x equals 7, and that changed to x equals 7 halves, what allowed you to do that? What did you do to both sides? When I ask you what allowed you to do that, usually the answer is wrapped up into what did you do? You divided, right? So the division property of equality allows you to do that, correct? Does that make sense to everybody? Would that work here? Can I divide the left by 1/4 and divide the 7 by 1/4? Absolutely. That will work. That will get x to be 1, or 1x, and it'll give you 7 to turn into 28. Division property of equality works there. But when it's a fraction, hopefully your Algebra 1 teacher taught you, if it's a fraction, what is easier than dividing by that fraction? Multiplying by its reciprocal. So Math Excel is doing in this one, it would look for multiplication property of equality instead of the division property of equality. You would, in retrospect, you could argue this, that if you put division, you are right, it works. Okay, because multiplication, division, or their inverse is multiplication is the same as, or sorry, division is the same thing as multiplying by reciprocal, that kind of thing. But when you're trying to get your homework done and you say, well, I'm dividing, I keep getting it wrong, try the multiplication one. That's what they're looking for. If it's a whole number up front or an integer up front, they're looking for division. If it's a fraction out front, they're looking for you to say it was multiplication. Okay? But the whole purpose of today, guys, is so that when we say something is true, we want to have a valid argument. We want to have an argument that has no gaps in it. Okay? We don't want to have somebody say, Mr. Fay, why is it this way? And I just tell you, because it is. Because I said so. Or because somebody else said so. Okay? When you ask me a question, on all of our mathematics, if you have enough math knowledge right now, I should be able to kind of explain to you why it is the way it is. Okay? I should be able to go through a kind of systematic process of showing you this is because of this, because of this, because of this. It is kind of backwards sometimes in mathematics because you've been told in like 6th grade can't divide by 0. It might not be until next year until you start learning about like asymptotes and stuff like that you really understand why you can't divide by 0. But eventually you'll have that ability to answer that question. All right? And that's what I want you guys to start thinking about. Start focusing on when you're in class somewhere or just in life in general. Just don't take things for what people say, right? Ask why. Okay? Now I'm not saying go home and mom says, no, John, you can't have money. Say, well, Mr. Fay told me ask why. Don't do that. I don't want mom calling me and get mad at me. Shut up. Okay? But ask what? Okay? Be interested or try to investigate things. Okay? And you'll be able to understand concepts and material a lot better if you do that. Do that.